Welcome back to the lecture on A-star algorithm for global path planning in the course Drone Systems and Control. So, in the last lecture we have gone through the understanding of global path planning, then we have differentiated it with local path planning. We have seen that global path planning is not real time, we have to do it before the mission starts. Then we have gone through some environment representations, and end of the lecture we have gone through one graph based search algorithm, that is Dijkstra algorithm, and we have solved one example. We can represent the environment like graph, and then the drone with the proper path planning can follow this Dijkstra algorithm based planning or planned trajectory and can follow it. But what we say here is that Dijkstra algorithm has certain limitations, and for that we are moving to the next concept called A-star algorithm. Okay. So, why it is better? It is better because it is called informed search algorithms, which is a heuristic guided search. It will be clear in the lecture. A-star algorithm characteristics, advantages and limitations we talk about, and then we tell that what can be the heuristic functions in drone navigation. Finally, we will end the lecture with one example. Okay. So, in path planning we have seen that the drones must navigate safely to the goals. So, one thing is safety, which is important, it should not collide with the known obstacles at least, and the second thing is that it should reach the goal to accomplish the mission. Fine. So, the vehicle, the autonomous vehicle or drone which is moving must avoid the static and dynamic obstacles using the onboard sensors. Okay, fine. Then plan a path from start to goal in configuration space, that is the requirement. Then it should avoid the collisions with the obstacles, it should get feasible path in the free space, and it should plan the path considering the kinematics or dynamics of the drones. However, with each of the any of the path planning algorithms, there will be some trade offs between optimality, speed and feasibility. When we take the constraints of drones, its kinematics or dynamics, then feasibility also becomes one issue. Not every path will be feasible to be tracked by the drone. Okay. Now, what is A-star algorithm? It is another graph search algorithm for finding the shortest paths. But if you see the graph, now you see that there are not only edge weights, we have some node weights also, right. We have some weights on the nodes like this written in red colors. So, A-star algorithm combines Dijkstra algorithm and greedy based first search algorithm. It utilizes a cost function and a heuristic function. So, edge weights are given as the cost function, and in node what you are seeing is the heuristics or heuristic function. Fine. So, it guarantees optimality with an admissible heuristic. What does that mean? We will discuss later. Then by A-star algorithm, the drone will try to pick a path, the pre-planning of A-star algorithm will try to pick a path for the drone which will like minimize the total effort and estimated distance. Okay. So, if it is going from one node to another, then there will be some distance associated. So, it will try to minimize the distance, that means shortest path is coming from Dijkstra algorithm, that concept is coming. Then the total effort, if it goes from one node to another node, then from the second node what is the total effort required to reach the goal, that is the heuristic which is coming from the idea of greedy best fast search. Okay. It is widely used in robotics, path planning of drones, etc. So, here it finds a path if one exists in a finite search space. Okay. Now, returns the shortest path with an admissible heuristic, which is very important. Okay. It uses heuristic functions to guide the search efficiently, explores the nodes based on the lowest total estimated cost. That means, it will have one cost based on the distance. So, it will visit a node n checking its distance from the previous node and the total effort required from node n to goal. Okay. Fine. So, what is the advantage of A star? It is it guarantees optimal if the heuristics are designed in a proper way. Then it uses the heuristic function to guide the search intelligently towards the goal. So, only shortest path is not the objective here, we have one additional criteria. It reduces the number of nodes explored compared to the ununiform search which was done in Dijkstra algorithm. How it is reducing the number of nodes? Because now it will consider the total effort from the nodes to reach the goal, which is included in the heuristic function. So, in that way the complexity is also reduced. Now, cost functions can be chosen flexibly taking into account distance, energy consumption, risk of collision, terrain elevation, something like that, which was not the case in Dijkstra algorithm. It was talking only about shortest path, right. Now, there are say efficient A-star algorithm is efficient for occupancy grid, which is very common in drone SLAM based drone navigation. Then it is perfect for navigating drone environments with fixed obstacles. Okay. As I was talking about the global path planning. So, if we know the map entirely, it is better, otherwise the conventional A-star algorithm will face challenges. Drones can avoid restricted zones by increasing node costs. So, it is very important to understand we are telling that heuristic functions will be playing some roles, and based on that heuristic function we can understand that what is the total effort to be put by the drone if it wants to move from that particular node to the goal node. Now, if there is a restrictive zone, we can design the heuristics in such a way that that particular node will never be visited. Okay. Fine. Now, with good heuristics and efficient implementation, A-star runs in real time on medium sized maps. For large maps, additional challenges might come, which we have to handle separately. So, in A-star algorithm, what we are having? We have a graph structure, fine. The graph will be having the nodes, edges, something like this, fine. Then there will be some cost function, the actual cost from start node to node n. Okay. So, if it is at start node S and it is moving to the node n, then it is the actual path cost. Like if there is some number say 10, then it tells that like it represents the distance, and based on that shortest distance is always preferable. But there is one more thing which is important in A-star, as I told, that is not only the shortest path, but some heuristic functions, right. Now, these heuristic functions will tell that what is the effort to reach to the goal from node n. Okay. It is the estimated cost from node n. Okay. So, Dijkstra algorithm tracks the actual path cost, and greedy based first search gives the guidance towards the goal. We combine both in A-star algorithm. First one gives the path cost, second one gives the heuristics, and with this additional information taken into account in A-star, it performs better compared to Dijkstra algorithm. Okay. So, what is the total cost? Total cost f n will be the sum of cost function and heuristic function, okay. And it guides the search toward the goal efficiently by balancing actual and estimated cost. This is the actual cost, this is the estimated cost. Okay. So, Hn, what is the heuristic in drone navigation? Hn estimates the cost from given node n to goal. Okay. So, this is start, this is another node n, and somewhere here the goal is lying. So, that is the goal node. So, if it is coming from the drone is coming from the source node to node n, then what will be here is the actual path cost, that is g, and the heuristic h associated to this particular node n, which will tell the total effort the drone needs to come from this n node to the goal node, this path. Okay. So, the drone navigation heuristic can be taken care of 3D environment Euclidean distance, it can be based on the kinematic constraints. That means, for some node to achieve or to travel by the drone, the turning constraints may not be enough, or the turning capability of the drone may not be enough to reach a particular node. So, for that the heuristics will be taking the shape accordingly. So, different constraints, angular costs can come into the heuristic function for a particular node, okay, node n. Also there can be some energy aware heuristics, like you can take distance between that particular node and goal, then it can be some scalar multiple of wind resistance. If it travels from n to g in this path, then it can be some altitude penalty. It can have certain no fly zones which will take according heuristic function, and based on that the heuristic final heuristics might take place. So, it can be a combination of different parameters also. Okay. So, in drone navigation, a drone must navigate from a start point to target location. Search space is represented as 2D or 3D occupancy degree. Then A star evaluates the feasible path by minimizing travel cost and estimated distance to goal. It can be distance or some other factors also, like energy, wind disturbance, something like that. Obstacles are avoided using validity checks during neighbor expansion. So, when from one node to the other node it is traveling, and then from that node it is going to some other node, then obstacle detection is done in this area in the neighbor expansion, and it is checked that whether the next node can be nearby, and accordingly the next node is finalized. Okay. The resulting path is a sequence of waypoints guiding the drone safely to the goal. Fine. Now, we will talk about one example, and it will be easier to understand that how A star is working and how it is different from the previously discussed Dijkstra algorithm. So, this is the graph we are talking about. It has nodes from A to J, A, B, C, D, E, G, F, H, I, J. With the nodes you see these values, these are the heuristic values of the particular nodes. Fine. So, from 10 A has a heuristic node of 10, means from reaching A to J, that is the goal, the effort is somehow represented as 10. Okay. Now, if it is 6 here, that means the effort is 6 represented, the total effort will be less than total effort from node F will be less than total effort from node A to reach the goal. Now, what the problem which we want to solve here is that find the most cost effective path. Now, we are not talking about shortest path. Shortest path was the intention to find in Dijkstra algorithm, right. So, we need a cost effective path to reach from start node A to final node J or goal node using A star algorithm. Okay. Fine. So, what we do here? We have step 1, we start with the current node A. Now, from A it can go to B here, or it can go to F, right. Now, A star algorithm calculates the total cost for node B and for node F. What is the total cost for B? If it wants to come to B, then it needs a path cost of 6 actual cost, and then the estimated cost is 8, which shows the total effort to reach the goal J. So, totally it becomes 14. However, in the same way the node cost the total cost for the node F becomes 9. So, it will try to minimize the cost in that way, and that is why F total cost for node F is less than B. So, going from A to F is a better option. Now, in step 2 it has come to F from A. Now, it can go to node G here or node H here, right. When again in the next iteration of A star algorithm, we find that f g has a total cost of 9 and f h has a total cost of 13. So, f g is better. So, the path is taken as A f g, fine. In the step 3, from G it can go to only I in the forward direction. So, node I can be reached from node G and I has like total cost 8. So, it will decide to go to I. Now, from I it can go to, from I it can go to J, H and E. When we calculate like this, from F from the node I to E, if it goes, then how it is coming, we have to calculate the total cost, that is 3 plus 1 plus 3, 3 plus 1 plus 3, right, plus 5. So, 3 plus 1 4 plus 3 7 plus 5 12 plus 3, total becomes 15, right. In the same way, for H we can calculate 3 1 3 and then this is the path length 2, and again the node is having the heuristic of 3 or estimated cost 3. So, it becomes 12, and for J it becomes 10. Since it is a goal node, the total effort to reach this node from this particular node is 0 only. So, we have 0, and then we get that f j is the least. So, it decides the algorithm will decide that next go to node j. So, that becomes the path, fine. So, now if we think from the very beginning that what happened here, we will see that the vehicle is coming from this point, starting node A and reaching J, right. It is coming by this road. It is coming from A to F, then F to G, then G to I, and A to F, G, I, and then directly J, fine. So, in this way the path is optimized in terms of the actual cost and the estimated cost, addition of that too, and finally it reaches the goal through that path, okay, fine. Now, what are the limitations of A star algorithms? We can in the previous slide what we have seen is that if we use A star algorithm for predefining a path for global path planning of a drone, we can get the path which will give the lowest cost. Which, what is the cost? The cost is the sum of actual cost and estimated cost, and accordingly if the path is prefixed, then the drone can follow it like waypoints. It from A it comes to F, then G, then I, then J, fine. But the performance degrades in high dimensional space or large search spaces. It heavily depends on quality of the heuristic function. So, as we are talking about in the beginning that the heuristic function should be admissible. So, if it is not properly designed, then the A star algorithm can give some faulty results which are not optimal in that way. Okay. Then can be memory intensive due to shortage of open and closed sets, then it may expand many unnecessary nodes in complex environments, that is also a problem. Okay. Whatever shortest node will be coming, it will take. It computes a single path once based on a fixed map. Okay. If an obstacle appears after planning, A star won't react unless rerun from scratch. That means what? When there is something not known or there is something based on partial information, A star the prefixed path will not be take those surprises into account, and it should rerun from scratch, that means from the start node itself maybe. So, it is not well suited for highly dynamic environment or continuous time systems without proper modification. Okay. A star is a graph based search algorithm for optimal pathfinding, that is how we can summarize it. It combines actual cost Gn heuristic cost HN. HN can take different forms depending on the applications, what kind of application we are going to have. Based on that, the heuristic should be like designed in a admissible way. It can guarantee optimality and completeness if proper heuristic is designed, widely used in navigation, autonomous vehicle navigation. Its performance depends on the heuristic quality and computational resources. Computationally it can go, though it is in a way gives better results than Dijkstra algorithm, but computational requirement may become higher if it is a very high dimensional spaces or large space. Okay. In its standard form, it is not designed for dynamic obstacles. So, if you want to modify A-star algorithm for dynamic obstacles, you have to do some additional steps, not scope of this particular course, but you can explore it by yourselves. Okay. So, the next lecture will be on RRT and RRT star algorithm, which is a sampling based algorithm, not the graph based search. I suggest you read A-star algorithm intensively from this particular source, which is a very reliable book in this particular domain. This is a MATLAB resource which will help you understanding how to code A-star algorithm in a proper environment which is involving a drone. Thank you. See you in the next lecture. In the next lecture, we will talk about sampling based path planning, RRT and RRT star.